Now I want to introduce you to, we're very happy to have him as a team member, Julian Stirling, who is really an expert in open toolchains and worked on the OpenFlexion microscope and the software system behind it, Git building.
So I'm Julian, as Peter said. So I'm talking a bit about what I was doing before the Open Toolchain Foundation and how we really saw that what we needed was an open toolchain. So I'm going to talk a little bit about the OpenFlexion microscope. So the OpenFlexion microscope, I know some people in the room have come and talked to me. They've seen it before, but for those who haven't, it's a motorized digital microscope that's designed to be laboratory grade. And most of it's 3D printed, but it's not like certain 3D printed pieces where you say, I'm going to measure a traditional microscope, and then I'm going to print the same thing and hope it's okay. And you know that the surface quality of 3D printed things is not the same. But 3D printing gives you this great geometric freedom to make shapes which you can't really make in other ways. So this is a microscope that is designed based around 3D printing to give you something which has limited assembly and which really takes advantage of those particular structures. And it's designed so anyone can reproduce it in the open. We're focusing on medical use. We've got partners in Tanzania who've been with us since the start of the design, but also on research and educational use. And so a great thing about openness is you can build a research community with it. So these are a couple of papers that we found online. These are people who've not only just built the microscope, but they've modified it and made it locally in their lab for what they needed. So somebody has made a super resolution microscope, somebody else an optical sectioning microscope, based on our designs without ever having to contact us and say, how do we do this? Which is fantastic. Microscopes are actually been built and used in over 40 countries. I particularly like that we have Antarctica. We have a photo which I could not find of somebody using it on the Antarctic ice to look at algae. And so in education, so this is a makerspace in Nairobi where they're making microscopes for educational use, for taking into schools. So you can see that you can bring a microscope into a school, and the great thing about a digital microscope is you're not saying, hey, peer down this little eyepiece. Can you see that thing? It's over there in the corner. Well, it's not even a corner, round over there. If you get it on a screen, you can get everybody round the screen. You can point at things. You can do a much better education with a digital microscope. Something that's fantastic about these guys in Kenya, which we can take no credit for, is that they're actually making the microscopes they're taking into schools from plastic bottles. They have a guy that cycles around Nairobi getting Dasani water bottles from the local cafes. They pull it up into little pieces, they grind it down, make it into filament, make the filament into microscopes and take it into schools. This really is the circular economy happening, and it's really exciting when the first time I saw them actually making the filament. So I said our main focus is a medical microscope. So why do you need a medical microscope? So what we're looking at here are red blood cells from a thin smear. You look at red blood cells to look for malaria parasites. So malaria still kills 500,000 people each year, most of them children under the age of 5, most of them in sub-Saharan Africa. And the gold standard for diagnosis is taking about 100 microscopy images and looking and counting parasites. And so this large image here is a stitch of multiple 8-megapixel images taken by our microscope, automatically moving through and stitching those together. But why do we particularly need to make an open microscope? So you can see here's Joram in Tanzania with the microscope, and we also have clinical partners in America. This is Daniel Rosen. But people say, why do you need another medical microscope? There've been medical microscopes for a long time. How much does it cost to buy one? Why don't we just buy someone a microscope? Isn't that easier? It costs $20,000. But as people in this room all know, what is the actual cost of running a microscope? It's not $20,000. What happens over time when you break one piece? You're going to need the parts cost, but far more important, the engineer travel. Zeiss aren't going to say, here's the instructions for how to mend your microscope, here's a spare part, have at it. They say, oh, we need to bring an engineer to fit that. Oh, there isn't one in the continent. Can you pay a business class flight for somebody to fly out to Africa? That's going to be a problem in Tanzania. You're going to maybe look at £10,000 for somebody to come out to fix one broken part. But if we can build a microscope locally, we can fix a microscope locally. And so what we're actually thinking about is, can we make a microscope design inside a university that is understandable by many And we want community to be able to suggest changes for different types of microscopy. We want all these different types for hobbyists, but we also want a medical product that can actually be used. And of course, medical products, we've gone through, we talked about liability the other day, yesterday. We had, we need the clinician control, what went into the design, the risks that we have to assess. You've got all of those medical standards to make sure that all of your documentation is up to date. And how hard is it to actually do this in the open? And remote collaboration is very hard. So this is one thing where what we've been doing is taking a design inside a university, making sure we've got very good records of it, and making sure that different people in different places know which parts are in the final design in what's going to be the medical design versus which are sort of community additions. But trying to get hardware engineers to use Git, quite problematic. So we spent a long time, this is a graph I'm not going to go into that I tried to use to explain how Git works, not particularly successfully. But one thing we found is it's much more than just the history of your design. So people talk about DevOps. We've heard people talk about things like the GitLab system that they're using in IVV. But we've got this cycle going through where not only do you actually store your design with your version tracking, but you're making sure you've got automation inside to make sure that what is in your design is what people are producing. You're taking the feedback, storing it in the same system, and doing all of your project management. And this allows us to make this wonderful automation system where we update parts of the microscope design, and automatically it creates the production-ready SDLs. Automatically it creates the renders. Automatically it creates the documentation. We've also got, in the same repositories, we've got our software, we've got our operating system, we've got our website, and an interactive selector, so if people are customizing the microscope, this is all generated automatically every time, so you don't have a human in the loop. And this is great. We were talking about cryptography yesterday. And so the Git hash, so you know exactly what version. So very important for a medical microscope. You need to know which version was made. And so we can actually stamp the cryptographic hash of the particular commit on the CI directly into the physical piece. So you know exactly which version of the design was made. And then after you've done that, you can go through and generate all of your documentation and make sure it's up to date. Now, doing that, we were a research group trying to make a microscope. And what did we spend most of our time doing? We spent most of our time, you might even say wasted most of our time, writing our own software to do the job we were meant to do. And that is not what we were paid to do. We weren't paid to write software for designing hardware. We were paid to make a microscope. And so I'd like to end this with saying, wouldn't it be fantastic if there was a foundation that could actually support that work rather than researchers individually having to design their own toolchain? And so on that note, I'd like to thank all of the different people that worked in the core team. We never all met together at the same time, so I had to make this wonderful little picture. And then also our clinical collaborators and everyone in the community that's fed back into the project. And yes, thank you very much.